Alright, looking at calculus and what it's for and what it's about, here's an example, an illustration. Kind of thing it can help us do. Kind of thing that'd be hard to do before calculus, pre-calculus, without these kind of concepts. So, let's think about a rocket taking off. Here we have grass, or dirt, concrete, and a rocket taking off. Beautifully drawn, beautiful artistry, best you'll ever see. So here's our rocket taking off. Of course, it's taking off. Okay. So, shooting up into space from the surface of the Earth. Now, when it's going, how does it move? What makes it go? Well, the thrust. And where do we get the thrust from? Fuel. Just like, how does a car go? The car is able to move because we put gas in it, or whatever. Different kind of cars, gas-powered cars take gas. So we got some fuel that's being burnt. But this thing's going up into space, and it'll be traveling for a while. Whatever it is, we're not doing rocket science here. We're just thinking about how some of this works, illustrates some ideas about calculus. I'll put links to stuff about more detail about this if you're interested, and then you can look at research papers and books about rocket science. But it's going up. That's a thrust, a force. So remember your basic physics, or learn it. F equals ma. A force, a push, causes an acceleration. You push something, you force on it, force it, it changes speed, or changes direction. Now, when this is going up, fuel's burning, just like you use gas, and you got to go to the gas station, put gas in again sometimes. You got to gas up. This doesn't do that, but it's still burning fuel. So what happens when it burns fuel? It's burning stuff, and that's mass. So there's less stuff here, less mass, and hence less weight when it's going. And if we make this simple, think about, okay, if this is a constant, let's say a constant thrust, then when this goes down, this goes up. Take a simple example. If this is 10 and this is 10, let's say the thrust is 100. Let's work on keeping it constant. If this is 9, like 9 kilograms instead of 10, then to get 100, we need 100 over 9, which is 11 and 1/9. Or if this is 8, this would be 12.5. And this is 100. And so when this is going down, the acceleration is to increase. And that's happening every split second. Fuel's constantly being used, continually being burned, mass is continually changing, and that's continually affecting this acceleration. And that's some stuff we need to know, because we learn in physics some things like how this relates to position. Take some simple equations like the height of the rocket will be the initial height. We'll just call it 0 for ground. It'll be like for stuff in general. Okay, initial velocity. This is 0, but just to go over the general equation, v naught t plus 1/2 at squared. This won't have an initial velocity. It starts at 0. We just have this part, but like the basic idea, the height would depend on that. Acceleration times time squared. But if this is not constant, if it's changing, then that affects how this is changing. And would you want to calculate that every second? What's the height of the rocket after fuel's gone for 10 seconds? Well, if it's been going for 10 seconds, then like without some calculus, we'd have to see what this is, like how it's changing every second, and how it affects this, and how it in turn affects this. And you got to go through a lot of iterative calculations. And imagine after 100 seconds, 100 of that, who would want to do that? That's a pain. We need more efficient ways to do it. Calculus helps us do that. And then the velocity is changing too. You know, not the initial, but the velocity later on. Because velocity is acceleration times time. Acceleration is a measure of the change in velocity. Could be magnetic speed or direction, as you'll learn later. Maybe you already have in physics. But that's why the acceleration is important here. It affects these things about where the rocket is. How high is it? What is it doing? And both of these are important because we got like little changes in mass. When this is a little change, just like in slope, delta y over delta x, you could have a little delta m, and that's going to affect, it's going to make a change in force. Okay. Change of mass, a change of force. It's like proportional to it. Related to it, as we'd say, without an equation. And there's other things you could look at too, but that's one thing that illustrates how when this is going up over a long period of time, the mass is constantly increasing, changing the acceleration, changing where exactly it'll be, changing the velocity, and that plays into other things as well. But that's a good illustration right there. But let's say, for example, another thing to consider is Newton's law of universal gravitation. This is just some constant. Mass of the Earth, mass of the rocket, which is changing, and that changes the weight, of course. Less mass, less weight, and so the thrust is to overcome less. Just like pushing a 3-pound piece of wood on a floor is easier than pushing a 50-pound piece of wood. Is easier than pushing a 1,000-pound. The more it weighs, the more force it's required to push against it. Same thing here. The more this weighs, the more thrust is required to push it up. But when this weighs less, if pretending the force is constant, then the thrust will give that more push upward, more acceleration. So we got this here. That's changing, changes that. All these complexities, which are super cool. And this R is the distance between the center of the rocket and the center of the Earth, like the radial distance. So we got the Earth here and the rocket here. And R would be from the center of this to the center of mass, not like geometric center, but center of mass to center of mass. The radial distance, as if it's like your radius of a circle. So that's the rocket's going up. It's changing. The distance between the center of the Earth and the center of the rocket is changing. And that in turn, besides this changing, that affects the weight also. When it gets up higher, like 50 miles, 250, it's still got some weight. It's just a percentage of what it was before. It's not weightless. I'll put some links so you can see why astronauts are weightless in space. It's because of how they're falling, not because there's no gravity there. That's like ludicrous. Gravity extends beyond. I can show you. You can like look it up on the internet. I'll put links. Talk to physics professors and teachers and stuff. Also talk to other people. And I recommend that. Think for yourself. Look things up. Do research. Please do not take things in isolation or take someone's word for it. Know on your own. That's what the Wright brothers did. So they were able to make a plane that would go far and turn. No one else could. Because the Wright brothers did research in a wind tunnel. They thought for themselves. Everyone else was following this coefficient that didn't work. They were just blindly following authority, not thinking. And the Wright brothers my computer like almost went to sleep there. But they thought for themselves. They were like Aristotle, Galileo, and Newton. They looked at the evidence of the senses to figure out what measurements and principles and ideas would work. And so they were able to figure that out, apply that to a plane, and make it go far. They thought for themselves. Please do that. Now here, if we take the surface of the Earth is about like R0, our starting point, about 3,960 miles. From the center. The radius, if you go from the center to some places on the Earth, it's about that far. And let's say we go 50 miles up. This plus 50, 4010. If we go 250 miles up from the Earth, add 200 to this, 4210. And if we do the math on this, if we take ratios, they come out to like comparing the square. The mass will be changing, but let's like just ignore that and make it constant. If you have G M over R squared over like R0 or the 50. Take the 50 G M over R initial squared. You see how the later relates to the initial. When we're dividing by a fraction, we flip and multiply. So we do, dividing by this fraction, we get this one. Flip it, multiply, and as you can see, this and this are the same. A number divided by itself is 1. They divide out, and so we get R sub 0 squared over R50 squared. Or do the same thing with 250, and we'd have R0 over R250 squared. So to see what percent of your weight you have here, 50 miles up versus here, 50 ain't very much compared to this. 250 ain't much compared to this. So it shouldn't affect it too much. So this, at this point, the weight will be initial over the 50 squared. And then here we have initial over 250 squared. Okay, and this over this squared will be about 0.975. And this over this squared will be about 0.885. Okay, so not much difference. When you're at 50 miles, you're still like 97% of your weight. So if you weigh 100 pounds, you'd weigh 97.5. Or 250 miles up, if you weigh 100, you'd weigh 88.5. Whatever your weight is, multiplied by 0.975, that's what you'd weigh 50 miles up. Whatever your weight is, multiplied by 0.885, that's about what you'd weigh 250 miles up. There's a formula. You can do the math yourself, look it up. So it's still got some weight when it goes up. So do astronauts. It's just a smaller percentage of it. But, the thing we want to think about here, it's just to illustrate it. It doesn't become zero. As I say, when the rocket goes up, it's increasing its distance from the Earth. The weight is changing a little bit. Mass is the same, but the weight will change. And the weight is a force. And how this force has to overcome this force is going to be changing. If this is constant and this is smaller, this is able to push it more. Okay? Every little bit of time. And again, that's going to play back into affecting the height and the velocity. which is super cool. That's some of the stuff we can deal with more efficiently with calculus, all this interaction. And then this is moving. And another thing you could think about is the air resistance. So as it's going up, we've got drag force, which would be something like the drag force, air resistance force will be like 1/2 density of the air. We usually use this rho thing in like physics to do in chemistry to deal with that, times the velocity squared. So we got the velocity there, which is changing. As this changes, this changes. And then you got this drag coefficient thing. And then you got the area, cross-sectional area of the rocket, which wouldn't change much, you know, the cross-section going up. So this is affecting it too. But another super coolness here is the density is changing as you go up too. I'll put links to this stuff and you can look it up if you want also. So this is density of the fluid, but it's not the same as you go up. When you go up, the density is constantly changing a little bit. It gets less. This gets less. When this is getting bigger to some extent. And so that's going to affect the force as well, the drag force. The higher you go up, the less this is, the less the thrust is to overcome. And imagine like bringing all this together and having to do that without calculus, having to do all these iterative calculations. That would be a pain in the rear. Or having to do like 100 calculations of all this different stuff. You don't have time to do it. It'd take like super genius effort on the part of some people to tabulate all this stuff and see all the interactions. Just amazing. But and the pressure at a certain altitude, I'll put a link, but it does change, and you can see some tables and some equations if you're interested. But there are some ways where calculus will help us deal with small little changes. So there are some small little changes we talked about, how one thing affects another. As I say, imagine how difficult this would be having to do a bunch of iterative calculations instead of having calculus, which helps us deal with changes and add up total sums with these integral things. We got derivatives and integrals, which help us deal with small, tiny changes, and then teeny tiny changes in how something goes, how it changes speed, or teeny tiny changes that add up to make some total sum. That helps us in here. So there's an example to think about when you're doing calculus. And then think about how it might apply to other things. Maybe some exercise, fitness, something else in physics, something in chemistry, biology. What about some biological system where things are interacting? Food for thought. Anyway, hope that helped. Peace. Thank you.